Welcome to the Slide Rule Survival channel, where we talk about mechanical computations using a slide rule. For this video, I wanted to introduce various slide rules I have in my collection. I'll start by talking about materials of construction. Then we will talk about layout of the various rules, different countries of manufacturer, and then we'll talk a little bit more about supporting documentation. To start, the various types of materials of construction included plastic, as you'll see on this Aristo rule. This rule in the center, a Deci-lon rule, contained both celluloid, and that's what the scales were on. And if we looked at it on the end of the rule, what you'll see is wood. That wood could be something like bamboo. The last rule I have on the table is a Pickett rule. This particular rule is in what Pickett referred to as the eye saver yellow color. Pickett also made rules in white if you desired to have them. The eye saver yellow supposedly lent a little bit more precision to your ability to use the rule. I don't know if that is true or not true. In any event, this rule was an all-metal rule, as we can see, and in essence, the one distinguishing feature I would note is that on the American type of slide rules, typically the cursor or hairline on the cursor had no special sorts of markings on it. On European rules, that was not true. As a simple example, on certain rules that you will see certain type of marks on the cursor, and they were designed to do different things. Putting this a little bit more so that you can see it, you'll have horsepower to kW conversion. You might have an area or diameter conversion and the like built right onto the cursor of the rule, thereby making it a little bit easier for you to do some very, very quick computation without having lots of settings of the rule and lots of manipulation of the rule. By contrast, we can see that this Pickett rule has no such markings, no such hash marks on either side of the rule. The other thing to notice on the slide rules is that they all have scales that are laid out slightly differently, and in some cases even the nomenclature for different scales changed. As a simple example, it's not uncommon on rules that A and B were used to designate the square root function or the square function. Having said this, not everybody stuck to that convention. Pickett, which had a tradition of kind of doing things the way they wanted to do it, actually used the square root symbol to denote anything that was to be used in a square root operation. In a similar fashion, for things like cube root, again, K was sort of a convention that a lot of people agreed to, but not everybody stayed with that convention. Once again, in the case of the Pickett rules, they didn't use that. They actually used cube root, and they had a different way of computing cube root. The other thing I wanted to point out was layout of nomenclature on the scale. Notice that on this Pickett rule, everything is typically with letters on it. And notice that the letters are on both the left-hand side and right-hand side of the rule. This is a duplex or two-sided rule, and we will see that the same convention is followed on this side of the rule. That we have the letters corresponding to each scale on both the left and right-hand sides. You'll notice that on this Deci-lon rule, an interesting feature that they did was they put everything associated with what the rule, the scale and the rule did. And what they would do is they would tell you a little bit about it with not only the name of the function with its alpha designation, but also the scale it was intended to cover on this side of the rule. And if we turn this particular rule over, you'll see that they sort of did the same thing in the sense that you have the letters here on the left hand side of the rule, and then on the right hand side of the rule they actually will show you the name of the argument using mathematical symbols. So that's one of the things that Deci-lon did. As I understand it, the Deci-lon rule was created by an ex-employee of Keffel and Esser, and that was, so to say, the way that they got around a lot of things relative to layout of the scales, in that they kind of showed you this is what we'll call a self-documenting rule, because you didn't even necessarily have to know the name of the scale. You just had to look for the function you wanted to use. So that's why that particular means of presentation was shown on the rule. I'm going to take this Deci-lon out of frame, and I'm going to put this Post Versalog rule in frame. Versalog was an American company. Having said that, a lot of their rules were made in Japan, as is this model. Again, this is one that had a celluloid type of finish. That's that white finish on the top, and it had wood. I'll pick up the rule just to kind of show you, and I believe it's bamboo as, so to say, the main material of the rule. The interesting thing about these rules was they decided to place the letter and the corresponding function all on the left-hand side of the rule on each side of the rule, as shown here. And I'll just turn this over, and we will see exactly the same thing on this side of the slide rule. Now, as an example for ease of reading, what the people at Post did with their Versalog rule, their claim to fame was, well, the sine and the cosine functions are complements of each other. So as an example, if you were interested in the sine of 6 degrees, that's the same as the cosine of 84. You'll notice that the sine function is in black lettering. The green representing cosine is this lettering here. So in other words, if I'm looking at the sine of 6, I'm actually looking at the cosine of 84. And in similar fashion, as we go up our scale, you'll see exactly the same thing on this side. So here's a situation where I've got sine of 50 is the same as cosine of 40, and so on. So that was one of the things that they did. So there was a lot of marketing to various constituencies, students or engineers as a simple example, to say, our rule is very, very easy to read and easy to use. So that's another example. Once again, I'm going to take the Post out of frame, and I'm now going to place another very popular rule in the United States called a Deci-lon. This is their Deci-lon rule. This is a later model Deci-lon. The Deci-lon, I believe, was in service from the early 60s up through the end of when slide rules were made. This particular rule, as you'll see, has many of the functions we've come to talk about: square root, cube root, our tangent function, our sine function, and here the nomenclature used was SRT for small values of sine and tangent. Notice on this particular rule that what they did was they gave you ranges to look at in terms of approximately what range the desired digits that you wanted to look at were. That's what that range is for you. It's sort of a little reminder as to how the rule will work and what it's set up to do. Whenever, by the way, something was in reverse, again, anything inverse was denoted in red, as shown here. What they did was, where they had sine and cosine, again, what they would do is they put cosine in red, sine in black. So here, this is the cosine of 84, sine of 6, cosine 83, sine of 7, and so on. So that would be an example of that, of how different manufacturers presented the information to you in different ways. Ultimately, one person realistically would never carry all of these rules with them. They'd have one and they'd get very, very familiar with how the look and the feel of it was laid out. So let's now proceed to do a little bit of compare and contrast in terms of layout, in terms of design, and things like that. For the Slide Rule Survival channel, for our purposes, a very big emphasis we're going to have is on simplicity and readability and intuitive feel for what the scale is doing and how we use it. So another big selling point for many different manufacturers was, how can you get to the answer that you want for a function that I want to evaluate around a given point without having what we'll call too many settings of the rule. The more times you manipulate the rule, whether I'm moving the slide itself, whether I'm moving the runner and the cursor, would be an example of setting the rule, the more error prone that you are. So that's an example where, again, layout of scale is very important. And further, the type of work that you're planning to do with the slide rule is also very important. If I'm going to do functions that involve vector computations, for our basic definition, a vector is a number that has both magnitude and direction, certain types of slide rules lend themselves better to that sort of computation than others. The critical thing is, probably a student, let's say a college student or something like that, probably would have only used what was in his college bookstore unless a teacher or somebody else had, so to say, guided the student as to what it was that they felt that they needed. The nice thing about a slide rule was the fact that it basically, once you picked it, it had almost all the functions on it. Sometimes, however, you might find that whereas today I might only need certain functions, like as is shown here, for my e to the x or e to the minus x, depending upon my range, I might later on decide that I might want other functions. And with a little bit of being clever about knowing math, you might know that you can use these scales to help you evaluate things like hyperbolic sine, hyperbolic tangent, or hyperbolic cosine. It just depended upon how the rule was laid out as to how easy it was to make the computation of interest to you. So we talked a little bit about layout, and in my definition, layout is, do I get the name of the scale? Do I get the corresponding, what the function looks like mathematically, right? Also, I'm interested in how easy is it for me to move the scale and manipulate it. The aristos tended to be easy to slide from side to side. They tend to be pretty easy to set my cursor. The one thing I do want to note is that even though they had nice hash marks, as can be seen here, here, and here, they're not always very, very easy to read. So they are there for you, and they're very convenient, and they can be a great time saver, but you have to compare that with your ability to know where you're going to set that hash mark on the cursor, knowing what it means and knowing where to get the corresponding answer. So that's sort of say the challenge. This rule is a very, very good rule for my limited experience in doing things where I'm computing a vector. It's very, very well set up for that. So that's the reason why I like this particular rule very much. What you'll notice is that everybody kind of laid things out a little bit differently. And again, they tended to call the same function different things. So as an example, on this Pickett rule, on this rule from Deci-lon, which is a Keflen-Esser rule, they had square root as sort of, say, a scale that ran from 1 to 2, and then the remaining values went from 3 through 10. Whereas on this rule, you were using A and B to compute the same function, and typically when you had a square root function, and we'll go into it now, you'll see that we actually have two repeating cycles from 1 to 10, and then from 1 to 10, right? So that's something that you might see. And again, like I said before, because Pickett liked to be a little bit different, they did things different than almost all of the manufacturers in terms of conventions. So you really had to understand how to make their rule work. It could give you some more accurate information as to computing a square root, but it kind of depended upon what you thought was important to you. So that's enough about what I'll refer to as layout for now. Another topic that I want to talk about would be the topic of precision. And there seems to be a lot of confusion between accuracy and precision. One can say that if I have a wristwatch and I have lots of little tick marks between the minutes, I can read an answer with lots of precision. So if I tell you that the time right now is 2:22 and 30 seconds, if I have enough tick marks on the watch, I can determine exactly where that is on my wristwatch. Having said that, that does not necessarily mean that the wristwatch is accurate. So as a simple example, if the watch says 2:22 and 30 seconds, but in reality the time is 2:27 and 58 seconds, we don't necessarily have an accurate device. The device is precise, but not necessarily accurate. And there was a lot of butchery, unfortunately, in slide rule manuals sometimes on this topic. What we can say as a general point is that a 12-inch rule, as one can see with this Versalog, would be somewhat more precise because of the fact that I can have a pretty fine resolution as to where digits are on the number line. By contrast, this Aristo rule is going to be somewhat less precise because obviously in the same number line, let's use our C and D scales, obviously it's harder for me to set a precise location for a number. So as a simple example, I can easily set, let's say 7.5 on that rule. I'm pretty sure that that's exactly where it's going to be. It's midway between 7 and 8. Now, if I decide I want to go, let's say, to 7.57, now that's a little bit between 7.5 and 7.6. And on this rule, you can't possibly get that precise. It's going to basically be by eye is how you're going to make that setting. By contrast, if I'm going to go to my rule here, I'll just line that up a little bit better for you. You can see that I can figure out, here's 7.5, here's 7.55, right? And a little bit past that would be 7.57. So this rule, it's pretty precise as to exactly where I'm going to set that particular set of digits. So that's what we can say about that. A different thing that a lot of people might get obsessed with, besides precision and accuracy, is the question sometimes asked is how many digits can you get out of a slide rule? From the research I've done, you typically can get about 3 digits of accuracy on a slide rule. And for most things in the world of engineering, as an example, that's pretty much more than enough of what you need. Let me illustrate with a quick point. Let's say we made a widget, doesn't matter what it is, but we can only manufacture the widget to a tolerance of 5%. So as an example, if the widget was 100 units long, well, you'll get some parts of the population that are 95 units long and some parts of the population that are 105 units long. So as such, the bottom line is if this thing goes to the thousandths place, which is what 3 digits of accuracy will be depending upon where you put your decimal point, you're never going to see that in terms of the real world implementation of your part. So that is a very, very brief discussion of precision and accuracy for our purposes in looking at slide rules. In this instance, I'd like to focus a little bit more on some features that I think are important for a slide rule user. One of the biggest things that concerns me as I look at a slide rule is how intuitive is the rule for me to use? How comfortable, what are the ergonomics or ergos I feel as I'm looking at it? Is it easy to work with? Is it rough on my hands? Those sorts of things. I would say that by far and away, picket rules, especially in iSaver yellow, are the most visually pleasing to look at, without a doubt. Having said that, my big issue with a picket rule is that their instructions are somewhat complicated and take a lot of patience to learn to use. So from a usability standpoint, if I don't have the manual for this rule, this is not something I'm necessarily just going to be able to pick up and use, let's say, as quickly as this rule. It does most of the same things. This rule does not do as many things as the picket, but the bottom line is, if it does 80 or 70% of what I want it to do, I might be better served with this rule over this one, primarily because what we'll refer to as the instructions or the rules to use it are not as complicated for us to do. This is fairly complicated, but also fairly sophisticated if it's used the proper way. The other thing I want to talk about besides that topic of ergonomics and of the issue of readability and of intuitive feel is also realistically what you might have carried with you to the field. More than likely, the pocket rules are rules that were designed that you'd have in your briefcase or rules that you'd have carrying on some article of clothing. So by necessity, you're not going to really want a rule that's too large to carry around. But like anything else, the trade-off was precision. So these rules pretty much could be used, so to say, to sanity check an answer or to give you somewhat of an idea as to what your answer is to be. For more serious work, you're definitely going to want to use a rule that's 10 or 12 inches long because of the fact that you're going to get more precision and it's a little bit easier on the eyes to read. I should point out that most of the time, the other big selling point that manufacturers had to slide rules was, well, by virtue of carrying a slide rule, this did not mean that I then had to also carry a book of mathematical tables. So for those of us who've been around a little while, the original way in which trigonometry was taught was one had to learn how to use tables to look up values of sine, cosine, tangent, so forth. A slide rule, of course, removes that burden from you. So that's a book that you don't have to carry, because in essence, your tables for your tables for trigonometric functions are right there. The same is the case for a logarithmic function, log base 10. The same is the case for functions of e to the x or e to the minus x. So right there, that was a very, very big selling point to owning a slide rule, because you didn't need a set of tables with which to do computations. That was the great part about it. The thing I'd also point out about materials of construction and usability, from what I've been able to find, is that slide rules with bamboo, I think, have a very, very nice operating feel to them. But the problem I've noticed is that in more humid or wet weather, the issue with a slide rule is that the wood will expand on you, or if it's very cool, the wood will contract, which means that you're not quite getting the ability to set it the way you want. Also, that's going to have an impact on the accuracy of the rule. Obviously, the more temperature sensitive the material, the more likely the rule is to warp, which then means that your rule, once again, even if it's so-called precise, it may not be as accurate. Another thing to consider in looking at slide rules was, quite frankly, how the rule was printed. If the layout of the scales is not aligned, it doesn't matter how good your settings are or how capable you are with manipulating the rule, you're never going to get an answer that's going to be right. This is one of the reasons why, even with slide rules, one has to understand how to derive your answer, especially if you were doing some sort of work that required you to get a decent amount of precision to your answer and a decent amount of accuracy to your answer. So it's extremely important, in my estimation, not only to be able to do a computation just using the rule and the mechanical algorithms, I'll call them, to set the rule, but also you should be able to check your work still using tables if you wanted to do so, if a calculation was that critical to you. So that's my thoughts on that topic. I think that the rule could kind of get you in the ballpark. This is going to get you a lot closer to the ballpark than, let's say, this or this. But the fact remains that most times you'd want to use tables if you were working on something that was very, very critical as far as the numbers are concerned. Because of the fact that you couldn't generate things to 6 or 7 decimal places, which is what a lot of people will do now, even though those additional decimal places many times are meaningless, the fact remains that one would want to check one's calculations. And on top of it, back when calculations were done like this, it wasn't uncommon to have people that's all they did, was actually check figures to make sure that they were right after an initial computation was made. So that was pretty important to understand how to do. Because of the fact that computations done by hand or even done with a slide rule were by definition manual, and so by definition time consuming, it was very important that the people doing those calculations really had a good feeling for what they were doing, because there was no ability to run, let's say, multiple scenarios if you had to run everything by hand or do everything by setting the slide rule 3 or 4 times. You had to very much have a good idea as to where you were going before you got to the final answer. I also note that because of the fact that there were systematic inaccuracies built into every computation, what would have been done was you would have produced a little bit more of what we'll refer to as factors of safety with every time we did something, to make sure that if we were worried about, let's say, the strength of a beam or the strength of a hook supporting a beam, you'd want to know that even with systematic inaccuracy of our calculations, maybe figuring something too small or figuring out something a little bit too large, that you'd always know that you had that factor of safety to account for the things that you may not know about. So that's one of the other great things that a slide rule did force people to do. So that's sort of a brief overview of the types of different rules that you might see or you might see us use during these presentations. I hope you enjoyed this discussion, and we look forward to seeing you again next time.